Hi there, this is Engineering Mechanics Dynamics, and I am Dane Quinn from the University of Akron. And I'd like to do another example dealing with Cartesian motion. So here we have a block, and the acceleration is given as x double dot. So x measures the displacement of the block. Its second derivative is alpha e to the minus sigma t. So the acceleration decays exponentially in time. If the block is initially displaced by a distance x0, right, so at time 0 we move the block over by that amount and release from rest, so the initial velocity is equal to 0, then I'd like to find the velocity and position of the block as a function of time. So in order to do this, we need to, of course, identify the position. Right, so let's define an origin here and a point on the block there. And then we'll draw the vector between these two. Right, so the origin will be O, the block will be P, and again the position is P with respect to O. So in addition, I will identify the directions I and J as horizontal and vertical, so that the position, velocity, and acceleration are easily written in terms of the measured coordinate x. And those are given as r of p with respect to O is x in the I direction. The velocity is v of p is x dot in the I direction. And finally, the acceleration of point P is x double dot in the I direction. So again, essentially, we're trying to relate the position, velocity, and acceleration to the coordinate x that was given in the problem statement. Now, x double dot is given again as alpha e to the minus sigma t. So with that, we can integrate with respect to time to find the velocity. So if x double dot is equal to alpha e to the minus sigma t, then I can write the velocity as the integral of that. So essentially, we will integrate from 0 to t the acceleration. Right, so I'll actually go ahead and write it in this way. Tau is a dummy variable associated with the integration. So in doing so, we integrate both the left and the right sides. So the left side becomes x dot of t minus x dot of 0, and this equals, well, the integral of this term, which is minus alpha over sigma e to the minus sigma tau, and then evaluated from 0 to t. So taking this expression, we can solve for x dot. And we find that x dot, as a function of time, is the initial velocity plus, well, when we evaluate this, we end up with alpha over sigma 1 minus e to the minus sigma t. And of course, the initial velocity here was 0. So we have the initial velocity as the following. Then we can integrate again to determine the displacement. Right, so let's go ahead and write the velocity, and I'll write it in terms of this dummy variable tau. alpha over sigma 1 minus e to the minus sigma tau. And then, once again, I'll integrate both the left and the right side with respect to time, from 0 to t. So when I do this, the left-hand side becomes, well, we have the integral of a derivative, so that's just the argument, x, evaluated at the limits of the integration. So x of t minus x of 0. And then we have this term evaluated over time. So in particular, doing this, so the first term becomes alpha over sigma. The integral of 1 is just t, and then plus 1 over sigma e to the minus sigma tau 0 to t. So when we evaluate these limits, we get alpha over sigma t plus 1 over sigma e to the minus sigma t minus 1. Right, so you can pause this if you need to and go through and work this integration out on your own. And so finally, x of t, remember the initial conditions here were the initial displacement was x naught. So x of 0 is equal to x naught plus this term that we got from the integration, alpha over sigma t plus 1 over sigma e to the minus sigma t minus 1. So finally, at the end of all this, we find that the velocity of p, again, is x dot in the I direction. So that's going to be from here, alpha over sigma 1 minus e to the minus sigma t in the I direction. Remember up here, tau was just a dummy variable for the integration. So now the independent variable is time, right? So that's why these taus look like t's down here. And also then the position r of p with respect to 0 is equal to, well, x of t in the I direction, which is from here, x naught, alpha over sigma, t plus 1 over sigma, e to the minus sigma t minus 1. Close those in the I direction. So essentially with this problem, we started with known acceleration, x double dot, and then we integrated once to find the velocity, which was x dot in the I direction. We integrated again to find the position, x in the I direction. In both of those integrations, we made use of the initial conditions, which were x dot at time 0 equals 0, and x at time 0 is x naught. So there we have a nice example of moving from acceleration to velocity to position. Thank you very much. Take care.